So far in class, as we've looked at some of these distributions, everything that we've seen so far would be what we would call approximately normal. And these approximately normal distributions, again, they're centered around the mean, and the notation for us for mean in these samples is x bar, and the notation for standard deviation for those is S for standard deviation. Now, here's where things are going to be tricky. So kind of think through this for just a minute. If we've taken good samples, we would use these statistics to estimate what we think the parameters of the population are, right? We spent the first week and a half of this class talking about how to take good samples. So we're going to kind of work under the assumption that if we're told that they've done a good sample, we're not going to be that skeptical. We'll say, okay, they've taken a good sample, so we think that we could take these pieces of data and talk about them as parameters for the whole population of interest. So keep in mind, finding actual parameters is very, very difficult, if not impossible. So we think about these, in a sense, as theoretical distributions. If we could do it, this is what we think the distribution would look like. Again, so many of these distributions are going to start to take on that normal shape. We've seen it even within our samples. They're approximately normal, but if we could take the population, take a look at the whole population, we'd almost get kind of this perfect normal distribution. So again, in theory, these distributions of the population are perfectly normal around a true mean and are spread out perfectly according to some kind of true standard deviation. And these theoretical values, we saw it yesterday, we saw in the previous video, there's what the mean is, mu, and sigma for the standard deviation. So these are what would be the parameters, right? If you think about it this way. So the parameters are referred to as mu and sigma, the mean and standard deviation. So again, the notation for these, the actual data, when you take a sample, the actual mean is x bar and the standard deviation is S. All right, when we did the jelly blubber activity in class, you guys all came up with your own x bars, and then we graphed them, right? Another way we could have done those graphs is putting a bunch of x bars on our dot plot over there. We used x's, but essentially you're putting your x bar, and then those things were spread out according to some standard deviation. Now, the true mean, this is what we talked about. This was that 19.4. That one wasn't really that difficult to find because there's only 100 observations. And there was a true standard deviation, which again, standard deviation, the average distance from the average. So in other words, if we were to take every single one of those 100 observations, figure out how far each one of them was from the mean of 19.4, average all those together, we'd have our standard deviation. So again, a great measure of spread, and it becomes very, very useful as we continue to move forward. So the one thing that all these curves, despite the fact that we have curve upon curve upon curve, in so many different places, the one thing that they all share in common is what's called the empirical rule. Some people refer to it as the 68, 95, 99.7 rule. And that's because within 1, 2, or 3 standard deviations of the mean, you get a certain chunk of the data. So 68% of the data is within 1 standard deviation. You can see in this picture right here. So we start to look. Within 1 standard deviation, you get 68%. Within 2, 95%, right? So here's the mean. Here's plus 1 standard deviation, plus 2 standard deviations, plus 3 standard deviations. And you go minus 1, minus 2, minus 3. So you get those percentages that play out. All right. So one thing to realize, as you go further out in the curve's dropping down, so you don't have quite as much area to cover, right? 68%, almost 2/3 of the data within 1 standard deviation. But then you continue to drop down as the curve drops down. And then beyond that 3rd standard deviation, technically this curve is going to keep going on forever. Right? We could be 5 standard deviations above or 6, but it's very, very rare. So it's a very, very small percentage of the data that's beyond 3 standard deviations. So if you go back and think, what does it mean to be in the 90th percentile of test scores? Well, for us, that means that you're in the top 90%, right? You're in the top 10%. You're better than, right? You had a better score than 90% of people. So we can use this empirical rule to start to kind of play around with this thing in terms of percentiles. Probably the easiest place to start, right in the middle. right? If you're right on the mean, that means you're in the 50th percentile. Think about it, right? Half of the data is below you. Now you start kind of backing out of this thing, right? You go up 1 standard deviation. You have 34% of the data is in here, right? Which means if you're exactly 1 standard deviation above, you're in the 84th percentile. Right? And you still have 34% here, which means if you subtract 34, if you're 1 standard deviation below, you're in the 16th percentile. All right? And then you keep working your way up. You can kind of fill in the gaps here. Just keep playing with these percentages. So if you're 2 standard deviations above the mean, you're in the 97.5 percentile. 3 standard deviations above the mean, and all they're really doing, so to get that 99.85, they're summing everything right from that observation below. So these are some of the common percentiles that you guys are going to kind of play around with. But how we're going to end up doing it, right? Here's an example with Army helmets. So Army helmets are normally distributed. There's a mean of 22.8, standard deviation of 1.1. So the first thing I would suggest that we do is we're going to go into, and we're going to write down, right? So this would be plus 1.1, plus 1.1, plus 1.1. And then from the mean, subtract 1.1, subtract 1.1, subtract 1.1. And we can start to figure out things along these lines. What percent of the helmets are between 21.7 and 23.9 inches? So 21.7 to 23.9. Well, that's within 1 standard deviation. Empirical rule says that that's 68%. Right? 21.7 and 25. 21.7 is here, 25. So again, you have 34% here, 34% here. And if you go back and you look on the previous page, 13.5 sitting here. So if we add all that up, 34, 34, 13.5, add another 13.5 to that, you have 81.5%. Above 26.1, very, very few observations up there. And I actually do remember that was 0.15%. So there's hardly anything up there between 23 and 24 inches. And here's where it gets interesting, because 23 and 24 are given values. So 23 is about right here. 24 is about right there. So you start thinking we're close to some of our given values, but they're not right on the exact values. Well, right now, as far as you guys know, the only way we can run this is guesstimate, and that's fine for now. Because in the next video, we'll start talking about how do we actually get that actual value. So for us, it looks like it's going to be maybe a little over 34, right? We're a little beyond that 34%. So maybe we go, I might say it's about 42%. And I'm just saying 42. It is what it is. So that's kind of how we're using it. And then if we want to talk about percentiles, what percentile is associated with 22.8? So 22.8 is right in the middle, so that would be 50th percentile. 19.5, so it's way down here. Remember, there's only 0.15% of the data, so that's the 0.15th percentile, so very, very small beyond that. And then 25 would put us here, and that's 2 standard deviations above. And remember, that's so we would need to get all the data from here back down. I might just be a slacker and go back and look at this one. That was the 97.5 percentile for 25 inches. So we eventually are going to get to the point where what happens if we're not exactly on the line like you saw in D? how do we get those exact values so we don't have to guesstimate, and we'll kind of work our way through that information.